Okay, our first function we're going to graph is pretty straightforward. It's f of x equals the square root of x plus 5. Rather direct. A simple way, quite honestly, is just to plot a few points and see what the behavior is. So what I did is I set up a little chart here, and we start inputting numbers. Let's start with 0. It's quite simple. And f of 0 would be square root of 0 plus 5 is 5. We can put in 1. F of 1 would be the square root of 1 plus 5 is 6. Okay. And then I like to go in the other direction, put in some negatives. Okay, if we put in negative 1, we get the square root of negative 1, which is imaginary. And since this graph is going to be only real numbers, we are going to ignore all the negative numbers. Okay. And then I could put in 2, but the square root of 2 is kind of a tough number to figure out. So what I'm going to do is I'm going to put in, let's put in 4. Square root of 4 is 2 plus 5 is 7, so 4 is 7. And let's skip up and let's put in, go up to 16. So if we put in 16 as x, the square root of 16 is 4, plus 5 is 9. So I used some perfect squares. And you can see how quickly the x moves relative to the f of x. Okay, so let's plot these points. We have 0, 5. And again, we're just doing a sketch. So this is 0, 5. Okay, and then 1, 6 would be 1, 6. And then 4, 7. And then 16, 9. And you get basically a graph that looks like this. Okay. And so that's a pretty quick way to sketch a graph. Another way is what I call using the parent function. And if you recall, the parent function in this case would be the square root of x. Okay, and if you graph the square root of x, you may be familiar. It starts at 0, 0, and it, of course, moves in the same direction. And that's what the square root function looks like. And what has happened between this one and this one? We simply have had a shift of up 5. So another way to approach this would say, look, here's the square root function, and here's an upward shift of 5, because every output you add 5 to it, and you could also graph it that way. The second illustration is a little more complex. We have the function g of x, which is equal to negative 3 times the quantity x minus 2 squared plus 4. And again, you could plot some points. That's one approach to take. Or in this case, what I like to do is I like to basically use the method of finding the parent function and then transforming it and translating it. So the first thing you have to do is identify the parent function. And from experience, or maybe just from recognition, you could see that the parent function is x squared. Okay, and if you were to graph x squared, you might recognize it's a quadratic, and it's going to look like this. It's going to basically go this way, and of course this is 0, 0, 1, 1, 2, 4, 3, 9, a very standard quadratic. Okay, and then now what you have to do is you have to examine this, the way it's been transformed and translated. Okay, so the first thing is from the previous example, we have a vertical shift. If you remember in the previous example, we had an upward shift of 5. This one is an upward shift of 4. Okay, so of course if we were to shift this up 4, it would look something like this. Okay, so that would accommodate the plus 4. Okay, and then the next thing you have to look at is, what does this x minus 2 mean? It's within the function. And what it's basically saying is that any x value you put in here, you're going to have to add 2 over here to compensate for the shift. So basically, instead of having 0 here, you would have to have 2 to have the same output. So what happens is our shift is 2 to the right. And notice this is negative 2, and it's to the opposite. So you have basically a shift 2 spaces to the right. So this was 4 spaces up, and this is 2 spaces to the right. So now our new graph looks something like this. Okay, and this point right here, which used to be 0, 0, is now 2 points over and 4 points up. So this is now 2 points over and 4 points up. Okay, and then finally you have this graph here, and what's happened? It's been stretched by a multiple of 3. So now let's actually draw it once more. So we're over here right now, okay, and this is 2, 4. And really now what's going on is it's suddenly every output is multiplied by 3. So it's going to be going up faster and faster. Okay, and then the last thing is notice how it's -3, which means that every output is not only stretched by 3, but it's become negative. So instead of having this negative value here, it's suddenly down here. So now what you have is you basically have an output that's going to look something like this. Okay, so that's kind of a rough draft of what we're going to get. So let's sketch this thing. Okay, let's start with, bring a straight edge here. Okay, let's start. Okay. Okay. As mentioned, you might remember this is going to be the vertex. Two units to the right, 4 units up. So 2 units to the right, 4 units up. So let's call this 2, 4. Okay. And again, we're going to shift. It's going to be down, facing down and stretched. Okay. So it's going to look something like this. Okay. And what's the exact value? Well, let's plug in 0 and find out. Let's make this 0. If x is 0, somewhere here, the y output will be 4 plus 8. This will be 0 minus 2 squared is 4, minus 12 plus 4 is minus 8. So it's going to be right here, 0 minus 8. So our graph is going to look something like this. And then, of course, it's symmetrical, so this should also be 4 minus 8. If we plugged in 4, in other words, 2 units here, 2 units there, 4. 4 minus 2 is 2, squared is 4, negative 12, negative 8. And it's going to look like this. Okay, and then you could find these points right here by setting this function equal to 0 and solve for that, but I'll leave that for you. Here's just a quick sketch. Again, the domain will be all real numbers. The range will be any y value from 4 and below. Okay, this is the third equation we're going to try to graph. It's 1 over the quantity x minus 3 plus 2. And again, it looks kind of odd. And the first instinct I would have is, let's plot some points. So if we did that, we would start plugging in random numbers and see if we can find some sort of pattern. Okay, and we'd have x and y. And we would say, well, let's try 0. This is 1 over negative 3 plus 2 is 5/3. Okay, and then we try, well, 3 doesn't even work. That's undefined. Okay, and then we would have, we can plug in a bunch of other ones. And it's a little more cumbersome. So what I like to do again is go back to using a parent function and recognizing what it is. And the parent function for this one is 1 over x. It's the inverse function. And graphing this is much easier. Let's quickly sketch a graph of 1 over x. Okay, here's our x and our y. This is x and y. And 0 is an asymptote, right? Because at 0 it's undefined, so 0 will have a dotted line here. Okay, and if we plugged in 1, it would be 1, 1. 2 is 1/2. 3 is 1/3. And it trends down this way, never getting to 0. And then going the other way, if this were 1/2, 1 over 1/2, we would invert and multiply, so we'd get 1/2 is 2, 1/3 is 3, and it goes up this way. Okay, and that's for the positive numbers. And then if we plugged in the negative numbers, we would have negative 1, negative 1, negative 2 is negative 1/2, negative 3 is negative 1/3, and it would trend this way. And then we'd have it go this way. So this is what 1 over x looks like. Okay, that's much easier to graph or plot points because you're just using simple numbers and there's just an x value. So let's take this graph and let's use this to sketch this graph. The first thing we're going to do is we're going to shift this up 2 units. Okay, so the way I like to approach this is we're going to shift the whole thing up. So that's going to include the asymptotes. Okay, so our new asymptote is going to be, our new horizontal asymptote is going to be 2. Okay, it used to be 0, now it's 2. And our new vertical asymptote, notice how we've got a -3 here, so we've shifted the whole thing to the right, okay, is now going to be x equals 3. Okay, this is x equals 3, which makes sense, right? You cannot have 3 in here because it'll be undefined. So we have our new asymptotes, and now we just use our same graph that we had before, and we're going to have a sketch that looks like this, and a sketch that looks like this. Horizontal shift, vertical shift, and that's our output. So let's do it one more time by itself. Okay, we have our y-axis, we have our x-axis. Okay, and we're going to put our asymptote. Our vertical asymptote is going to be x equals 3. So this is x equals 3. Our horizontal asymptote, notice this is going to approach 0 as we go positive to infinity. And it's going to approach 0 from the negative side as well. But our horizontal asymptote will be y equals 2. And from the sketch before, we know we're going to have something that goes up like that. And then down here as well. And of course, I like to pick some random points to see if I'm correct. So let's take a look at this point right here. This is x is 0. So 1 over -3 is -1/3. So this should be 5/3. So this is 0 5/3. Okay, it's below 2. Okay, and then here we could actually plug in a number and determine what 0 is. And this would have to be, this is 0. So this would be -2, which would mean this would have to be 2.5, 5 halves. So this is 5 halves, and on and on. And you could test points up here as well. But basically, the whole point of this graph is recognizing if you know the parent function, it's a lot easier than trying to input values into a complex equation such as this one.